Gentlemen, in part 1 of my talk, I spoke to you about the design considerations as related to masonry structures. Now, in the second part of the talk, I shall be talking to you about the design considerations as related to preventive maintenance of RCC structures. We covered the first 3 phases, that is structural design, the common aspects as related to structural design, and the masonry structures in part 1. And in this part, we come to the RCC structures. Now, the basic aspects that affect the design of RCC structures are the idealization as to what is the structure going to be idealized as. Is it going to be a grid frame? Is it going to be a simply supported structure? Is it going to be a space frame, a shell structure, etc., etc. After having decided that, we decide the boundary conditions based on the actual situation on the ground, whether the hinges are going to be provided, whether it is going to be a fixed support, whether at the support or at the junctions. Then you got to have the specifications for concrete as decided by the environmental conditions, the load considerations, the stress levels. Then you have the important aspect of detailing, as I spoke to you about in the part 1, as to that the drawings are the language of the engineer. So, you got to consider the aspect of detailing, that the detailed structure should be understood, the drawing should be able to be followed on the ground. Then you have the criteria of deflection, the crack width consideration, the problem of the inverted beams, the aspect of the long corridors, and the thermal response, particularly in this part of the country where the winter temperatures and the summer temperatures are so widely variant. Now, before we go on to discuss each of those aspects that I have just listed, we must understand that the structure behaves the way it is detailed and not the way it is idealized. You may plan to have a simply supported condition at the support, but you may actually be providing the reinforcement of the column and the beam to go into each other. This condition actually will be a fixed condition and not a simply supported condition. So, these aspects I shall explain as I go by, but this is a very important aspect that you must not go wrong in idealizing something else and providing something else on the ground. Now, the underlying principle of RCC, gentlemen, is the theory of cracking, because unless the concrete cracks in the tension zone, it will not be able to transfer load to the embedded steel. So, you got to understand that process and thereby provide for various conditions that we will be coming out subsequently. Now, this is a very commonly observed sight, gentlemen. If you would notice, you have a crack at this junction. Now, this crack between the parapet and the roof slab can very easily be avoided . These are the potential crack lines that you already know, the elevation. This is the parapet and the roof wall roof slab junction, and this is the edges of the lower slabs. Now, these are bound to crack because of the differential behavior of the wall as respect to the slab. So, if you provide an RCC fascia at a slightly extra cost, this junction would not crack up. If you have a slab bearing to the full width of the wall, this is definitely going to crack up at these places. Now, these places should be filled up with elastomeric sealants, and should you do that, this kind of unsightly cracks that you saw in the previous photograph can easily be avoided. Now, coming to the problem of boundary conditions. Now, this place, if this bar and this bar are just left like this, if this bar is taken inside and this bar is taken inside, makes all the difference, whether it is a fixed condition or a simply supported condition. In RCC structures, gentlemen, a truly simply supported condition cannot be arrived at. So, you got to have a question of partial fixity. Then you have a very commonly observed problem of providing a plinth beam which is not originally catered for in the design. Now, this plinth beam has a lot of load on this, imposes a lot of load over here, and this reduces the stiffness, rather modifies the stiffness of this part as well as this part. This changes the amount of moment that is going to be attracted to either side. So, you got to be very careful. If you are to provide a plinth beam, provide it at the design stage and not at the construction stage. Then this same thing, if you are providing a reinforcement like this, it is a hinge condition, but if you are providing reinforcement like this and this, do not know what condition is going to come out with. So, you got to be very careful as to the actual detailing as related to the boundary conditions. Now, gentlemen, this is a very commonly observed site. This is the underside of a RCC overhead water tank. You have poor concrete, reinforcement exposed. This is a very commonly observed observation. Now, you see this patchwork and all this is to conceal the honeycombs. If it was a poor workmanship, it would be only here, but this is the thing that you observe on all these column beam junctions. So, this is the result of heavy congestion of reinforcement. This can be avoided by providing large size diameter bars, lesser number, grouping the bars, and also providing a highly flowing concrete by using proper plasticizers and a good slump. Now, the damage caused to the partition walls by virtue of heavy deflection. Frame structures are supposed to have panel infill walls. These panel infill walls are supposed to be constructed later on, but the builders on the site, just to avoid the formwork at this place, they make the panel wall alongside, and the beam is made to rest directly on this. When the load comes, it reflects, and obviously you find these cracks taking place. So, you must make sure that this panel infill is constructed later on and should have a groove all around to restrict that cracks into that groove, which can be repaired later on. Now, when we spoke about limiting the crack widths, cracks are bound to occur because of the inherent nature of RCC, but if the crack is within the cover, is got no problem, but in case the crack extends beyond the cover and goes beyond the reinforcement, this is going to lead to corrosion of reinforcement over there, and that is where the deterioration of the RCC is going to commence. So, at such locations, you must provide a proper coating or a paint covering, and that coating or a paint covering should be elastic enough to cover the crack width. So, that much should have the crack bridging capability and not be a rigid and an inflexible coating. Now, the problem of inverted beams, gentlemen, they cause problems in waterproofing and terrace drainage, and the potential cracks in the tension zone will lead to leakage and corrosion of reinforcement. This will be further amplified in the next slide. You have the problems of roof drainage. What happens to the water that gets accumulated over here? It can only be transmitted into the longitudinal direction. Sometimes what people do is provide pipes to drain the water through this, which is not an effective way. it can get blocked with even the smallest of the leaf or the paper that flies onto the roof. Now, you can provide the waterproofing over here fine, but what do you do about the waterproofing on top of this? Now, the problem of cracks and long one-way slabs. If you have ever tried to notice long corridors in the school buildings, office buildings, hospital buildings, particularly at the topmost floor, you would find that there is a regular pattern of cracks in the long transverse direction. This can easily be avoided, but firstly we want to understand as to why these cracks takes place are because of the thermal response of the slab at that place. Because the outside temperature and the inside temperature, the gradient is so much during the day and the night that at every 2.5 to 3 meters, the tensile stresses of concrete are exceeded because of thermal movement. So, that is why this cracks takes place. Very easily you can look after them by providing a heavier temperature reinforcement. Now, there is another problem as related to large floor panels, particularly in factory and industrial buildings. You have at the corners cracked up portions. Now, how does that cracks occur? In the first stage, the expansion of the floor slabs that take place, the movement of the floor slabs is restrained at the corners, and they are made to move inwards. In the first stage, the ends curl up, and in the second stage, these ends under the load of the service conditions, they crack up and you have a broken floor, a very common observation in industrial buildings. Now, all these things when we know are going to occur, we must find a solution. Drawing analogy from the electrical circuits, very common to provide a fuse in the circuit. Now, the fuse performs the function that it blows off whenever the current exceeds. So, instead of blowing off the whole system, you know where the fuse has gone off, you can remove the problem and replace the fuse. The same analogy, if we extend to our civil engineering structures, we can avoid a lot of problems. We can insert dummy fuses and we can insert structural fuses. To explain this, I will come to the further slides. A portal frame, this is going to sway under load, whether it is wind or our earthquake condition. This is going to create that shear stress and an extra amount of force from both the sides. This is going to drag, the drag forces are going to crack up like this. This can very easily be avoided by providing a dummy groove all around and filling that groove with a compressible material like an acrylic filler or any other filler which is convenient at that location. Now, the concept of the structural fuse, gentlemen, you have this bending moment diagram, the points of contraflexure. At the point of contraflexure, you provide extra reinforcement. I have not shown the normal reinforcement for the design, I have only shown the extra reinforcement. Now, these are going to be the potential crack areas during severe earthquakes. So, this extra reinforcement is not going to provide any moment resistance, but at the same time is going to provide a heavy amount of extra shear resistance to the structure, with the result that when an earthquake takes place, this part will crack up and relieve the stresses from that place, but will not at the same time allow this panel to fall down. When this panel does not fall down, a major amount of damage has been saved and loss of life can be highly minimized. After the earthquake, you can always repair this and put the structure back to use. Now, having considered the structural aspects, we will come to a few commonly overlooked aspects of design which are useful for the maintenance point of view. The first one is the shaft for the sanitation and the plumbing. access for maintenance, upturned box shaped fascias, and access for periodical services. Now, the upturned fascia, gentlemen, is a very common observation. We have this upturned fascias, but what happens to the water that gets trapped inside? They normally provide a small hole for the drainage. This hole gets blocked, with the result that water pools in over here, adds to the load, causes problem of seepage and dampness from this place and this place. This can easily be avoided either by avoiding this fascia, providing a downturned fascia, or if at all you have to provide a fascia like this, provide a clear cut slit over here, so that it does not get blocked and water gets drained off. This is another common problem in the case of your plumbing stacks. You have the soil waste pipes. Very often we have seen that there are no rung ladders to go up. So, how does the worker or the tradesman go up to do any repairs? So, you must have these rung ladders, then you have an access door, and the size of the space should be adequate for a man to go up with his tools. Otherwise, this is not only meant for hiding these pipes, they are meant for maintaining this area also. Now, gentlemen, this kind of a repair job, if you are not looking after the commonly observed points that I have sought, is a very common sight. Repairs cannot be avoided, but they can certainly be minimized. A word about the cement grade. Cement grade, gentlemen, people are now publicizing. The big factories are talking of Virat Shakti and Buland Shakti. You tell me, what is the purpose of providing 53 grade cement in a masonry structure where the strength of the brick is only 70 kg per centimeter square? The high grade, high strength cements have a high heat of hydration, and the high heat of hydration is going to lead to cracking and other problems on the ground. So, there is no point in using these high grade cements. These high strength cements are meant for special structures where special considerations are taken and very high strengths are required from the concrete. So, avoid using these gimmicks, and advise your other lay friends also. Another thing, gentlemen, is being publicized these days is Bina Swade cement. When people talk of Bina Swade cement, people understand that it is the cement which comes from their fireplace. It is not the cement, the ash which is coming from the fireplace, it is the fly ash that is being used, and fly ash, as you and I understand, is a thing which is useful for the cement. It reduces the heat of hydration and imparts many other property to the cement, which makes the concrete more durable. So, this wrong advertisements, wrong publicity gimmicks should be guarded against. Now, gentlemen, I asked you a question relating to what was civil engineering, and we came to the conclusion that civil engineering is simple common sense, because Slocum could construct a Bakranakal dam without any formal education. Now, I ask you as to what is common sense. Common sense, gentlemen, in my humble opinion, it is a sense that is rather uncommon. Please try and make it a little more common. To conclude, anything can be done, but you first must have an observant eye. Analyze if you see anything going wrong. Not only going wrong, if you see anything good, analyze why the thing is good, learn from it. Try to solve the problem. Instead of pointing a pointed finger of allegation, try to solve the problem as to why a thing went wrong. Having solved the problem, learn for future. Now, gentlemen, I come to the quality motto that every engineer, for that matter, must follow. The quality of work should be such that if you happen to pass by the structure 10 to 15 years later, you should be able to proudly tell your companions that you have been associated with the creation of that structure. It should not be the other way around, that people are trying to find as to who made the structure and you go about hiding yourself. This more often than not is the case, gentlemen. If you follow this, probably you will have better structures at a lesser cost. When I say lesser cost, it is related to the maintenance cost also. So, with that I come to the end of my talk. Thank you.